Dear colleagues, I am Всеволод Bahayenko from Institute of Cybernetics in Kiev, and the topic of my presentation is a parallel algebraic multilevel preconditioner with approximate inverses by basis matrix method. I will start from some brief introduction in the context of this research. The need to solve linear algebraic systems arises in mathematical modeling of a lot of physical phenomena, in particular when jointly modeling processes of different speed. In many cases, linear systems have ill-conditioned sparse matrices of large size, and in these conditions, iterative methods are most commonly used, but however, they exhibit serious convergence problems. The main method used to improve the convergence is the application of preconditioners that are the matrices whose multiplication on sparse matrices leads to the decrease in the condition number. Since an ideal preconditioner is an inverse matrix, many of them are built as its approximation. The most commonly used methods for constructing preconditioners are incomplete decompositions, incomplete inverses, and multi-grid methods. We study algebraic multilevel iteration method that belongs to the later class. The speed of this type of preconditioners is low compared to other types, and the time spent on their application takes most of the time spent to obtain linear system solution. This makes crucial the development of parallel schemes for these algorithms. While the algebraic multilevel iteration is shown to have a good performance on shared memory system, its parallel implementation on cluster systems and more generally distributed memory systems are poorly studied, and the presented study is trying to fill this gap. So let us first look at the general scheme for the algebraic multilevel iteration preconditioner application. Our problem is to solve the linear equation system preconditioned by some approximation of its inverse matrix as shown on the slide. In algebraic multilevel iteration preconditioner, we split the matrix into 2 by 2 blocks, doing it lower upper factorization that is represented through matrices Schur complement. Approximating Schur complement, we use the simplest first order case here. We obtain a recursive subdivision scheme. Fixing the size of diagonal blocks, we get the matrix partitioned as it is shown on the slide. The scheme involves multiplication of the inverses of diagonal submatrices that can be computationally costly and can lead to numerical errors when inappropriate algorithms are used. Our idea is to replace submatrix inverses by their incomplete analogs that are built using the incomplete basis matrix method. This method is proven to be effective for ill-conditioned matrices and is similar to Gram-Schmidt orthogonalization. It performs incomplete transformation, restricting the set of matrix elements that are changed. In the process of linear system solution using some preconditioned transpose-free iterative method, incomplete inverses of diagonal submatrices are performed once per system solution. It's usually called an initialization procedure. Further, the two-step two-cycle scheme is used to multiply matrices on vectors while solving the linear system. To make such an algorithm run in parallel on distributed memory systems, we applied the data partitioning scheme shown on the slide 4. Here, each of row blocks of submatrices is distributed onto the system of processes by blocks of rows. Each process stores blocks of rows of submatrices and can perform multiplications that arise while applying the preconditional in parallel. The example of such partitioning with 3 row blocks and 3 processes is shown on the slide 4. Using such a partitioning, we construct a parallel algorithm of preconditioners application that have 2 parts. The first part is an introductory part, performed once per system solution, on which incomplete inverses of diagonal submatrices are obtained in parallel. We use the ability of the basis matrix method to assess inversion accuracy on its iterations. We set the accuracy threshold, and if incomplete inversion accuracy falls below it, we perform complete inversion that requires much more computational time but ensures total accuracy of the solution. For this purpose, we construct for each process the sequences of submatrices to make them evenly loaded as far as it possible. This is ensured by approximately the same number of non-zero elements that are processed by each of the processes. Before performing calculations, processes exchange the values of matrix elements to make them completely stored within the memory of a single process. Then complete or incomplete inverses are done by the processes in parallel. And finally, processes exchange the values of inverted matrices to restore the initial partitioning. The second part of the algorithm is the parallelization of the cycle of multiplication of preconditioning matrices on some vectors. The considered partitioning scheme allows to perform such multiplication using a known parallel algorithm for sparse matrix vector multiplications when matrices are stored in the compressed row storage format. We use such a format for store all sparse matrices in the algorithm. Additional synchronization, however, are needed in this case because in the algebraic multilevel iteration, the vectors are needed to be multiplied by a series of matrices with possibly different fill-in pattern. For the constructed algorithm, we obtained theoretical estimates of its performance and successfully tested these estimates in computational experiments. So let's move to the testing part, to the computational experiments. For testing purposes, we consider the problem of modeling stress-strain state of soil under dam, using a model of dynamic consolidation of saturated soils in the domain that is depicted on the slide 6. The problem was discretized by the finite element method, and we have 8 unknown functions here. While forming a linear system, the rows were ordered to form blocks related to a single unknown function. Performing diagonal scaling of rows, we obtain matrices. They have the properties of non-symmetricity, that have a block structure, high fill-in factor, and high condition number. So we use the linear system obtained on the first iteration of simulation and solve it with the preconditioned biconjugate gradient stabilized algorithm. The properties of the matrix are given on the slide 6. Performing the tests, we at first examined the properties of the sequential algorithm, determining an optimal block size for matrix partitioning and an optimal value of incomplete inversion threshold. Talking about the size of blocks, its decrease led to a large amount of auxiliary operation and small matrix and vector multiplications, while block size increase leads to a substantial increase in the time spent on incomplete inversions. The found optimal value of block size was between 125 and 500. That corresponds to the obtained theoretical estimate. The change in incomplete inversion threshold also influences the performance in two ways. Its increase leads to a less number of completely inverted diagonal submatrices that lowers algorithm's accuracy. On the other hand, it also lowers initialization time. These effects were taken into account in obtained performance estimates, whose accuracy was tested during the computational experiments. At second, we performed parallel algorithm testing to determine an optimal number of processes and checking the corresponding theoretical estimates. Computational experiments were performed on the cluster of the Institute of Cybernetics. We used 8 core nodes and 1 process to 1 core mapping. Talking about preconditioners, multiplication, and vectors, the maximal speedup was equal to 24% on 8 processes and block size equal to 500 elements. Total speedup of linear system solution was significantly greater than the acceleration of the algorithm multiplication on vectors. It is due to higher scalability of the parallel implementation of the initialization procedure. When we reduce the block size, this time becomes smaller, but the need for a larger number of synchronization while doing matrix vector multiplications reduces algorithm performance and scalability. So we can conclude that the proposed parallel algorithm is an efficient solution only when a small number of computational resources is allocated. In the last series of tests, we compared the performance of the proposed algorithm with the efficiency of known algorithm implemented in Hyper software package. The complexity of the considered testing problem is proved by the fact that the only combination of iterative solver and preconditioner implemented in Hyper, which allowed obtaining solutions of the required accuracy, are the generalized minimal residual solver and the algebraic multigrid preconditioner. The proposed parallel preconditioner was used with the previously found optimal values of parameters and was faster than the algorithms implemented in Hyper when the number of processes was less than 20. However, the scalability of the proposed parallel algorithm was significantly lower. So, in conclusion, we can say that we have successfully constructed the parallel computational scheme for the modification of algebraic multilevel iteration preconditioner, obtained the theoretical estimates of its performance indicators, and experimentally verified them. Conducted computational experiments showed that the proposed parallel algorithm, compared to known solutions, had better performance for significantly ill-conditioned linear systems when solving them on a small number of computational resources. Thank you for your attention.